Hi guys, let's take a look at some exponential applications. In this section we'll be working with exponentials and logarithms to solve some application problems. We've already seen exponential applications in some earlier sections where we looked at the compound interest formula and the continuously compound interest formula dealing with money. That can still be in some problems in this section, but primarily the problems in this section where we'll be looking at exponential functions, they'll be revolving around population growth and radioactive decay. They basically use the exact same formula. It's just typically in population growth you're talking about a positive growth rate, and radioactive decay, of course, a negative growth rate. Let's go ahead and look at population modeling. It says that we can estimate the growth in a population using the model. The population at times t is equal to the original population times e to the growth rate k times t, where t is your time, and could be in terms of days, months, years, depends upon what the problem is stipulating. Now, this p sub 0, as I said, it's the original or the initial population measurement. Now, I put k in my formula up here. You're going to see in some problems that they call the growth rate r, and in some problems they call the growth rate k. You need to get used to seeing both of those variables as the growth rate. And again, that growth rate could be relative to the percentage of growth per year, hour, day, could be even minute or second. It depends upon the problem. Time is going to be your time in units, and again, those units could be any one of these. P of t is going to be your ending population. The population at times t, it will be the output of the future population at some future time t. So now, let's see an example of this. If I look at the problem here where I'm asking you or telling you the function p of t is equal to 340 times e to the 0.15 t. I'm telling you that that's going to model the population of bacteria according to a controlled environment. Now, in this environment, times t, or time t, is measured in hours. Okay. First of all, what is the initial population measurement? You could just see by the location in the problem, obviously, your initial population or your original population has to be the coefficient of the exponential. It has to be 340. But now, just seeing how that plays out in your formula and the reason it's 340, if you tried to plug a 0 in, you say, well, your initial population occurs when t is 0. So look what happens if you plug a 0 in for t. You'd have 340 e to the 0.15 times 0 power, and we know that that's just going to give us e to the 0 power. Then we know any number to the 0 power is 1, so you just get 340 times 1. You say, well, obviously, yes, the original population was that 340. You can either think of it because you can plug in a 0 and get the 340, or just because you recognize anytime you have the coefficient of the exponential function, that will be the original amount of your population. Now, this population, according to this model, has to be growing at a rate of 15% per hour. You've got to be able to see that from the problem. In your exponential function, whatever that decimal rate is, that's either the rate of increase or decrease of your population. In this case, 0.15 means 15%. Remember, in order to convert from decimal to percentage, you move the decimal place over 2 places. So I can say, well, 0.15 represents 15%. Now, it's growing at a rate of 15%, and you must get this next part. How do I know it's growing at 15% per hour? Because it's 0.15 times t, and it specifically says t is measured in hours. So I know, hey, this growth rate is growing at a rate of 15% per hour. Now, if that were 15% per year, that's much, much slower. This growth rate of 15% per hour, that's going to increase enormously fast. In order to see that, I'm asking you, what is the population one day or after 1 day of observation? So if the original population was 340 and it's growing at a rate of 15% per hour, then 1 day we know is 24 hours. So we can say, well, then this problem is just asking me, what is the population 24 hours later? So P of 24. You could say, well, it's going to give you 340 times the exponential function e to the r times t power 0.15 times 24. When I did that on the calculator, 0.15 times 24, just 3.6. Then you can say 340e to the 3.6 power. That's going to give me 12,443.3997. Now, if I wanted to check that with the calculator here, be no problem. I can just say 340 times the exponential function e. And notice I'll just put it in this format right here, 0.15 times 24, just like that. And I'm getting the 12,443.3997, just like we needed. Now, in a problem like this, though, you need to keep in mind that what we're trying to do is round to the nearest number, because we can't really have 0.39971 of a bacteria. So you just say, well, round to the nearest number of bacteria, which in this case is going to be your 12,443. Now, when I look at the next part of this problem, it's saying, when will the population reach 20,000 bacteria? So keep in mind, I know after one day, after 24 hours, it's going to reach 12,000 bacteria from an original population of just 340. So it's certainly not going to take very long to reach the 20,000. It grew from 340 to over 12,000 in 24 hours. So how many hours is it going to take to get to 20,000? Well, I know that 20,000 is my population at times t. So I just say I'm given the population at time t. I must be able to solve for what t is equal to. So I put 20,000 in the place of p of t in my equation, and that's going to equal 340 e to the 0.15 t. In order to solve for the exponent of an exponential function, you must get that exponential function by itself. So please understand, in order to get rid of 340, you must divide by 340 on each side. I'll see some students that want to subtract 340. That is not 340 plus e, it's 340 times e. So in order to get rid of it, you must divide. So I'll say 20,000 divided by 340 is equal to e to the 0.15 t. Now I take the natural log of both sides, and remember, why don't I put that e anymore on the right hand side? Because e and natural log are inverse functions. They cancel each other out. So when I take the natural log of each side, sure, my left hand side has a natural log of that fraction, but my right side, the natural log and e eliminate one another, and I just have the 0.15 t. So now this makes an easy equation to solve for t. I can just say, well, t is equal to whatever this natural log is worth here. And remember, I want to have an exact expression for an answer. So do not go into your calculator and get a decimal for this in this step. I would like to see an exact expression for t. So t is equal to this natural log divided by 0.15. Now that's the exact answer for t. Our calculator approximation for that, we'd come in here and say, well, we know we're taking the natural log of 20,000, and I'll go ahead and create a fraction just so I can fit it all on one line. Alpha y equals enter. So I have the natural log of, and I'll put the fraction inside the natural log, 20,000 over 340. I'll close out that natural log. We're dividing that by 0.15, and I can see, okay, 27.1636, and so notice over here the 27.163613 is our nice answer. Now you'll see I went ahead just for fun. You don't have to do this, but I put that answer into hours, minutes, and seconds. So if you needed to do that, all you would have to do is take this answer. If you wanted to know, well, first of all, you already know the answer is in hours. So 27 hours, you subtract off the 27. Now you say, what portion of an hour is this? Well, you know there's 60 minutes in an hour, so you multiply this by 60. And you say, okay, so that's where he's getting the 9 minutes. So I say 27 hours, 9 minutes, and now how do I get the 49 seconds? Well, I'll subtract off 9. I've already accounted for the 9 minutes. Now, how many seconds? You multiply this by 60, and you can say, well, it'd be 49.006 seconds. You could keep on breaking it down if you wanted to even go further than seconds, but this would be plenty. And that's just for fun anyway. I don't think any of the problems require you to do that. Up next, tried to have a little fun with this problem. Let's say we have an example where I tell you the population of Metropolis, according to a 2005 census, was 13.8 million. In 2010, the population had grown to 16.2 million. Assuming the population grows according to the model, the population at time t is equal to the original population times e to the kt power. Construct a population model for Metropolis. So let t equal 0 respond to the year 2005. And again, why are we letting t equal 0 correspond to that year? Because that's the very first population data that we had in the problem. So we have to consider 13.8 million as our original population at time equals 0. So time equals 0 corresponds to your 2005. Now, what I need to do in order to get a population function, though, you need to find what that growth rate is. So you use your data presented in the problem. We know 5 years later in 2010, the population was 16.2. So I can say the population at 5 is equal to 16.2. So that's going to have to equal your formula, your original population, 13.8 million, times e to the k times t power. Well, you don't know what k is, but you do know what t is. 5 years later, it was 16.2. So we get 16.2 is equal to 13.8 e to the k times 5 power. That's just going to give me e to the 5k is equal to 16.2 divided by 13.8. You had to divide by 13.8 to get rid of it, multiplying the e. And now you can just say, well, now we can get rid of the e on the right-hand side by taking the natural log of both sides. I get the natural log of that quotient is equal to 5k. So then I can see, well, k is just going to equal that natural log over 5. And when I evaluate that here on my calculator, I would just say, well, it's going to be, and I'll again do a fraction. And I'll have the natural log of the fraction. And I have 16.2 over 13.8. I'll close out that natural log. And then we divide by 5. Please notice that's where I had my value of k, the 0.03206,853. Now, from this you are supposed to construct a population function. Well, this is your growth rate. It's growing at a rate of roughly 3.2% per year. So now I do not want to have any rounding error, so I put every bit of that value of k up into my exponent. I say, so the population function is, the population at time t is equal to the original population in 2005 of 13.8 million times e to that growth rate k times t power. Now, it's asking you to estimate what the population was in 2012. Well, you just say, if the original population in this problem was the year 2005, this is 7 years later. So the population in Metropolis in 2012 would have been, you say, according to this model, it's the population 7 years later. All you're doing is you're plugging 7 in for t into your function up here. So it's pretty much just a straightforward plug it into your calculator problem. We'll get 13.8, and then I have times e. The e, I just go second natural log. And then the 0.03206,853 power times 7. Put that up in the exponent just like that. Pretty easy. And you say, well, this is going to give you your 17.27306,414. And now, again, remember, this is not just 17.273 people. So I'll keep the decimal value there. And then you say, well, these numbers were measured in millions of people. So that's 17.273 million people there. Okay, now, up next, I'm wanting to carry off of that problem and say, well, okay, how long would it take for the population to reach 20 million? I already know in 7 years it reaches 17.273 million. So it's not going to take many more years for it to reach 20 million. Well, I just set it up. Your population at time t is equal to 20. Set that equal to your original population, 13.8 million, times e to the k times t power. You said, all right, no problem. You get rid of the 13.8 by dividing it on both sides. Then you get rid of the exponential function by taking the natural log on both sides, and you get the natural log of that quotient is equal to what was just in the exponent, the k times t power. Then you can say, well, now you can solve for t by dividing by this value of k on both sides. And you just say it's going to be t is equal to the natural log of 20 divided by 13.8 divided by that growth rate k. And I'll say, well, once again, I'll go to my calculator here and type this in. I have a fraction, so I had alpha y equals enter. And in my numerator, I'll have the natural log of a fraction, alpha y equals there. And I can say I'm going to have 20 divided by 13.8. Whoops. Not all in the fraction like this. Since I created a fraction, I don't need to divide within my fraction. 20 divided by 13.8, and now I need to go up and make sure my numerator is correct. Now it is. So 20 divided by 13.8, I'll arrow out of the fraction and close it out. I'm dividing that by 0.0320683, and I know when I do that, earlier I got 11.57. Let's see. Yes, 11.57096.011. So, and again, remember, you'll need to put the units in this case. In this case, time was measured in years. So you'd say, well, a little over 11.5 years later, the population is going to reach 20 million. Now, we've been talking about population models thus far. The next thing that this section will talk about, or one of the other things this section will talk about, is radioactive decay. Radioactive decay is, again, it's just an application of exponential functions. If I say something has a half-life, all that's telling you is the amount of time it takes for that mass to be 1/2 of whatever the original amount was. For example here, let's say I tell you that some initial mass of 1,000 grams has a half-life of 20 years. Okay. Then if I try to scale out what the size of this mass would be over years, notice every 20 years it cuts in half of its size. So if whatever this particular isotope is, if it had an original mass of 1,000 grams, after 20 years it would have 500 gram mass. 20 more years later, at 40 years, it'd be half of that for 250 grams. 20 years later, it'd be half of that, 125 grams, and 20 years later, 80 years total after the beginning, it'd be half of that for 62.5 grams. So we're going to be finding formulas to represent this exponential decay, and our main formula is that you can say the model of any mass at times t is whatever the original mass is, times e to the negative k times t power. Now, this is just like the formula that we had here for the population growth. It's just typically, whenever you have population growth, you know it's probably growing in population, so so the k value is positive, or you could say r is positive. In this case, your growth rate's always going to be negative because it's just decreasing in size. So we go ahead and put the negative up in the exponent to show it's going to be a negative percentage decay each period cycle times the amount of time. Now, so mass is your m sub 0, that's your initial mass. And sometimes you'll see r to represent the growth rate, sometimes k. And I shouldn't have said growth rate. It's going to be a negative growth, so decay rate. And again, it could be k or r. And then the time is going to be the number of units, of course, the time in units, and then the mass at times t. That's your future value that you're looking for. Again, I'll continue with the Superman theme here. And let's say if we have kryptonite has a half-life of 8 days. And you know Lex Luthor is planning on using a sample to kill off Superman. Lex currently has a 400 milligram chunk of kryptonite. I'm asking you to construct the mass function for Lex's kryptonite chunk. Okay, well we already know that the mass at time t, according to my formula up here, it's just whatever the original mass is, which is 400 milligram chunk in this case, and then times e to the negative kt power. Well, the only thing I need in that function is to know, I don't know what k is. It doesn't give me that in the problem directly. That's okay, because you can just say, well, what you're told here is that the half-life is 8 days. So it's going to take a time of 8 units in order for 1 milligram to become 1/2 of milligram. That's where this is coming from right here. If I set any original milligram of chunk of this kryptonite, it's going to take 8 days for that mass to reduce to 1/2 of its original size. So the half-life formula I come up with is that the ending time is going to be 1/2 of whatever the beginning was. So I say 1/2 is equal to 1 e to the negative k times 8 power. Now please notice, I'm just pulling that straight out of this function. The ending mass is 1/2 if the beginning mass is 1, and your e is raised to the negative k times t power. Well, t, it said, was 8 days in this problem. So everything from here is coming directly from that formula as well. Now, I'm using this to solve for k. So I can go in and say, well, you don't even have to worry about dividing by 1 on each side. You just have 1/2 is equal to e to the negative 8k. And then you can say you can get rid of e by taking the natural log of both sides. And then once I take the natural log, I can solve for k by just dividing by negative 8 on each side. When I took the natural log of 1/2 divided by negative 8, I got my value there. Let me show that here on the calculator. I'd say it's going to be the natural log of, I'll just do 1/2 this time. Close that out. I'm dividing that by negative 8. And so notice, guys, I'm getting that 0.0866433,976 answer, just like I did earlier. And so now beware, that does not mean that it's growing. This is k value that you plug back into your formula where you have the negative in front of it. So now when I'm saying, what is your mass formula for this chunk of kryptonite? We say, well, the mass at time t, and where t is measured however many days later, the mass at t days later is equal to the original mass, 400 milligrams, times e to this negative k power times t. So what this is telling me is that this chunk, it's decreasing in size by about 8.7% per day. Now, with that in mind, we're trying to find out now if it's decreasing in size by approximately 8.7% per day. For the next part, let's say we say 20 days from now, the mayor of Metropolis is giving Superman the key to the city as a token of appreciation for all the lives he's saved over the years. Lex wants to place his kryptonite chunk on that key to enact his nefarious plot. If at least 50 milligrams of kryptonite are required to kill Superman instantly, does Lex have enough? So you say, well, all we need to know from this fairly long word problem is that this is trying to find the mass after 20 days. So you just say, well, our basic formula that we just found on the previous page, the mass at times t is equal to the original mass times e to the negative k times t power. Now we're trying to find the mass at 20 days. So you just plug a 20 in for t. Pretty straightforward here. So when I do that here on the calculator, I'm trying to not get the glare from the light above. We have the original mass. Maybe if I put it over here. Yeah, there we go. 400 times e, second natural log to bring up the e. And you can say, well, that's going to be the negative 0.0866433,976 times 20 power. Well, times 20. You just put that right up in the exponent with the decimal. And whenever you do this, you'll get to your 70.711. I rounded to 3 decimal places, of course. Now, I actually put the units on that incorrectly. This should be milligrams, not kilograms. So regardless, though, the problem said that he needed a 50 milligram chunk. Well, he has a 70.7 milligram chunk. So you can say, yep, Superman is doomed in this scenario. You thought it would come out to where it would be like, no, he's going to be okay because Lex doesn't have enough. Not in my example. Let's look at another one here. I say an isotope has a half-life of 850 years. How many years to the nearest tenth will it take to decay down to 70% of its original mass? Now, I can actually see I went to the nearest, instead of tenth, I went to the nearest thousandth. Typically, I like to go 3 decimal places, so I'll just ignore that in my formula. I went to the nearest thousandth. But how many years to the nearest thousandth will it take to decay down to 70% of its original mass? Now, one thing that I want you to do in problems like this is make sure your answers make sense. So an answer that wouldn't make sense in this case is, I'll get students, they'll say, oh, it'll take 1,000 years or 1,200 years or 2,000. Those answers make no sense in this problem, and that you need to understand why. The isotope has a half-life of 850 years, so that clearly tells you it's going to take 850 years for it to be 50% of its original size. So we're not wanting to reduce all the way down to 50% of its original size. We're wanting to reduce down to 70%. So you say, well, if it takes 850 years for it to reduce to 50% of its original size, then it's not going to take as many as 850 years to reduce down to 70% of its original mass. So that's what I put here. We know the answer is less than 850. It has to be. So, okay, in order to see that answer, just like the last problem, you have to find the rate of decay first. So you say, well, your half-life formula, the mass is worth 1/2 of its original value of 1 850 years later. So we get the formula 1/2 is equal to e to the negative k times 850. That's going to give me negative 850k is equal to the natural log of 1/2. Then I can say, well, then k is equal to the natural log of 1/2 divided by negative 850, which that's going to give me a scientific notation. So let me make sure I show that on here. I'll do natural log of 1/2. We're dividing that by negative 850. And when I do that, I'm getting the 8.154672712 e negative 4. Please remember that e negative 4, that means times 10 to the negative 4 power. Or you could just think of it as, well, there's going to be 4 zeros before the first number you see here. Now that's 4 zeros including the 0 to the left of the decimal, which we typically don't write. So I thought of it as 0.000, so there's really 4 zeros there if I include the 0 to the left of the decimal, and then the number that you see on the calculator. So here's my growth rate. Extremely slow, I should say decay rate, extremely slow decay rate. It's going to take 850 years to reduce down to half the size at this decay rate. So now I put this value of k into my function, and I can see, well, I'm going to have whatever the original mass is, which I'm just going to call 1. Why do I want to call the original mass 1? Well, you weren't given an original mass in the problem. You don't need an original mass in the problem, because all you needed to know was that the ending amount is 70% of the beginning amount. So mass at times t is 0.7. If the original mass is 1, and then you can say e to that negative k times t power there. Now I need to solve for how many years it's going to take to get to 70%. So all I need to do is take the natural log of both sides. The natural log cancels out the e on the right, and I'll get my exponent negative 0.0008154672712t. To solve for t, I divide by that ridiculously long coefficient that t has, and I can say t is just going to equal the natural log of 0.7 divided by that growth rate that I had. Now, one thing I could do to make this easier on the calculator is I could just say, well, I'm going to go in and do the natural log of 0.7, natural log of 0.7. I'll have to remember to close that out. Now, instead of having to type that denominator in, I'm just going to say I'm going to divide by this number here. Now I need to be careful if I do that because I know I had to make that negative. It's not negative right here, so I'm just going to say divided by, and I'll hit the negative button on my calculator, divided by the negative, and then I'll say second negative to pull up that last answer. So all I did is hit negative and then second negative to pull up the last answer, and no problem. My calculator tells me, yes, this is going to take 437.3871969 years. I just rounded to 3 decimal places, which is typically what I ask you to round to, 437.387 years. And again, remember, that's that many years to reduce down to 70% of the original size. Pretty cool section here. You may see some other problems with Newton's law of cooling in this section and stuff, but even with that different application, the problems are solved identically to the way that these problems here are worked. Please let me know if you have any questions. I'll be glad to help.